I'm very glad to announce the talk of ionosphere, especially covering the structure, variation, and its phenomena by Professor K.N. Iyer, former professor and head, Physics Department, Saurashtra University, Rajkot. This program is by Space Education and Research Foundation, Ahmedabad. With these few words, let us listen to Professor K.N. Iyer.
Start off from this point. So, as we said yesterday, the balance between the ionospheric production and loss processes results in an electron density n, which varies with altitude or height h, and that graph showing this variation between n and h is called the NH profile or the electron density profile. The adjoining picture here shows one such electron density profile, which is a typical one. But we also know that Chapman's theory assumes single component atmosphere and monochromatic solar radiation. However, in practice, there are many atmospheric constituents, as we saw yesterday, atomic oxygen, nitrogen, etc. There are also different solar radiations in the different wavelength regions of the electromagnetic spectrum coming from the sun. These give rise to an electron density structure with distinct regions or layers named as D, E, F1 and F2. So the profile here shows the variation of electron density with respect to height. The y-altitude, the y-axis is the altitude or height, and the x-axis is the electron density or number of electrons per unit volume, marked in log scale, 10 to the power of 4, 10 to the power of 5, 10 to the power of 6, etc. So here we see there is a peak at about 100 kilometer, and this peak of electron density refers to the E region, and below that we have the D region, and above the E region electron density decreases and it again starts increasing, and it reaches a sort of a ledge, not a very clear peak, but a sort of change of slope in the profile, and this is called the F1 layer. And then after that, again electron density clearly increases and reaches a maximum somewhere here at the point called marked as H max, and the maximum value of the electron density there will be designated as N max. And then further that, above, the electron density decreases with respect to height. So this is the typical nature of the electron density with respect to height. This is as a result of the production rate varying with respect to height and the different loss processes operating at different heights. Now, in this picture, some dashed lines are shown here, which is giving the sort of boundaries or transition from one region to another region. And here, in fact, the height of the region of the ionosphere above H max is called topside ionosphere, and below that is the bottom side of the ionosphere. So we have the different regions, D, E, F, and F itself is split up sometimes into two, F1 and F2, and then the topside ionosphere. The picture also shows what are the major ions in these regions. For example, in the E region, it is molecular ions, O2 plus and NO plus. In the F region, it is atomic oxygen ions, O plus, and in the top side, it is O plus and also H plus. So as we can see here, as you go to higher heights, the mass of the ions decreases. So that means the lighter ions occupy the higher heights and the heavier ions occupy the lower heights. So this is the typical electron density variation with respect to height. Now let us see what are the ionizing radiations and ionizable constituents or neutrals that give rise to these different regions. The topmost layer is the F2 layer, which is produced by the same radiation and the same ionizable constituent as F1. So let us see what is producing F1 layer. So the solar radiation in the wavelength range between 20 to 91.1 nanometer, it is ionizing atomic oxygen. That is what we saw, the O plus is the main ion there. So in the F1 layer, and same thing is happening in the F2 layer also. Below that, the E layer is produced by ionization by radiation in the wavelength range just longer than the F1, 91.1 to 102.7 nanometer, which is also in the UV range. It ionizes the molecular oxygen. One strong line, spectral line in this region is the Lyman beta emission from the sun at 102.6 nanometer, which is just within this range, and that strongly ionizes the molecular oxygen. In addition to that, there's also another source, the soft X-rays of wavelength between 1 to 20 nanometer, which ionizes all because its energy is so high, it exceeds the ionization energy of almost all constituents. Therefore, it can ionize all, including the molecular nitrogen N2. So therefore, you get N2 plus and O2 plus as the major ions there. However, the N2 plus does not remain so. It undergoes further reaction and it gets converted to NO plus. And this radiation is important at solar maximum because there is a solar activity variation in the intensity or flux of this radiation. Now below that we have the D layer, which is produced by hard X-rays, means of X-rays of shorter wavelengths, 0.1 to 1 nanometer, which can also ionize all, and it is highly variable. For example, when the sun is disturbed, when there is a solar flare also, there's a large increase in the flux of this radiation, and therefore, at that time, you get large production of ionization in the D layer. Another source for D layer is 121.6 nanometer, which is one of the strong line emissions called Lyman alpha, which ionizes nitric oxide in the D layer. So that's a major source of ionization. There's also another radiation, 111.8 nanometer, which ionizes a particular metastable state called 1 delta of the molecular oxygen. Now, still below D layer, at heights of about 60 to 50 kilometer, the ionization is produced by charged particles in, for example, the cosmic rays. We yesterday discussed the production by energetic protons and electrons. So the very energetic charged particles in the cosmic rays, they can ionize all the constituents there, but the flux of these particles is very little, and therefore it produces only extremely small electron density at these heights. So these are the sources for the different layers. Now this graph further shows a bit more in detail how the electron density profile varies with respect to height. So you have the D layer here. I'm sorry, the picture is not very clear, so you cannot, you might be able to see D marked here. So this is the D layer, and this is the E layer up to this peak here. Then you have a small F1 layer there. Then you have the F2 layer there, and then we have the top side there. So at each height, what is the major source which is ionizing? For example, cosmic rays at lower heights and the lower part of the D or the C layer, then X-rays, then Lyman alpha, then again longer wavelength X-rays or soft X-rays, then Lyman beta. So like that, the various radiation that we mentioned in the previous slide, at what height they are producing ionization, that is indicated here. And so the EDE, F1, F2, and top side nomenclature is also shown here. And the major ions are also marked here. For example, in the E, it is O2 plus and NO plus, as we discussed in the previous slide. Then at F2 region, O plus is the main ion. And in the top side, at lower heights, it is O plus. A little up because of the diffusive separation, O plus becomes less important, and He plus helium dominates, and therefore the dominant ion there is He plus or alpha particles. And then the still higher heights, about 1,000 kilometer, it is still lighter constituent hydrogen, and when that is ionized, you get H plus there, and H plus is nothing but, or the ionized hydrogen is nothing but a proton. Therefore, this region also can be called or is called as protonosphere. So these are again the various ionizing sources, various nomenclatures, various positive ions, and the how the importance of the ions varies with respect to height. The lighter ones becoming important at higher and higher heights. Now the production rate, what is the rate of production? How many ion electron pairs are produced per unit volume per second? That is shown here in the x-axis. The y-axis is the height here. So by various sources, for example, this graph shows the production rate by cosmic rays. This shows the production rate by this molecular oxygen being ionized. Then this is for the combined production rate for EUV, extreme ultraviolet, plus Lyman beta, plus X-rays, and so on. And this is the one graph for photoionization by Lyman alpha. So all these are the sources. So the important point here to note is this last curve shows the total or sum of all these production rates. If we look at the total curve, then we see that below about 90 kilometer, it is this curve which is contributing to the total, that is photoionization of nitric oxide by Lyman alpha. And above about 100 kilometer, the ionization by EUV plus Lyman beta plus X-rays, that is this curve is contributing to the total. So thus, the different height ranges have different contributions from different sources. Okay, now we pass on to the next one. We said in the talk yesterday that the ionized component is only an extremely small part, something like 1/1000th of the neutral composition. So here a comparison between the neutral and ion number densities is shown. The panel A shows the variation with height of the number density of the neutrals, various neutrals like atomic oxygen, molecular nitrogen, argon, their minor constituents, etc., helium, etc. And the total is also shown by this broken line curve. So again, the curves are almost parallel, below about 100 kilometers representing the homopause, and then each has a different variation with respect to height, that is the diffusive separation in the heterosphere. Now, this panel B shows similarly the variation with height of the various positive ions, N plus, He plus, H plus, O plus, N2 plus, and so on. And the last curve here, marked E, actually is representing the variation of electrons, the concentration with respect to height, concentration of positive ions as well as electrons. And as we said yesterday, the ionosphere is a weakly ionized plasma. For any plasma, the total number of positive charges and the total number of negative charges should be equal for charge neutrality. Therefore, at any height, the sum of all the positive ions, concentration of positive ions should be equal to the concentration of the electrons. So in this height range, the O plus curve is, sorry, so the O plus curve is dominating in the F region, and similarly, the sum of these NO plus etc. will be equal to E in the lower part. Another point to note here is that the scale here, of course, is different. The number density of neutrals is expressed in number per meter cube, whereas this is number per centimeter cube. So that makes a difference of something like 10 to the power 6 between the conversion factor between per meter cube and per centimeter cube. Apart from that, you will see that these numbers are much higher. That is, neutral concentration is much higher than the. So even if you apply for that conversion factor, the ion concentration will be something like 10 to the power 3 to 10 to the power 4 less than the neutral concentration. So this is to illustrate this thing. Now, part of today's talk is the first part is the structure, which we have just now completed, and now the different kinds of variations taking place in the ionosphere. So ionosphere is not a static layer. Its properties or changes with respect to time of the day because it is very much controlled by the sun. It also changes with respect to season. With respect to height, we have already seen the profile, etc. So let us briefly see what are these variations. So this diagram here illustrates the variation of the parameter called total electron content, that is the integrated value of the ionization in the ionosphere as a function of the local time here. So this kind of variation is called diurnal variation, that is variation during the course of the day. So each block, the leftmost block is for the winter season, this is for the equinox season, this is for the summer season, this is measurements from a station, equatorial station in India, Trivandrum. So the measurements are taken for the year 2004. So we see that you take any curve, there's a red curve which is the mean variation, and then the green curves are the variation for each day. For example, if there are 20 days of observation in November 2004, there will be 20 such green curves which are superposed one above the other. And so the vertical extent of this green curve is a measure of how the parameter varies from one day to another day. That is called the day-to-day variability. So the green curve indicates the day-to-day variability, and the mean curve indicates how during the course of the day the electron content varies. So we see that it attains a minimum around 4 or 5 o'clock in the morning. Then when the sun rays start, it starts increasing, reaches a maximum in the sometime in the afternoon, and then it decreases. So this is the typical diurnal variation and the variability of the parameter at the equatorial station. It is true for other latitudes also. Now this further shows the what is called seasonal variation, that is from one season to another season or from one month to another month, how the parameter varies. So here in the x-axis we have shown the local time. This is measurements taken at a location near 120 degrees east longitude, somewhere in East China or in that region. Then the y-axis is the months, January, February, March, etc. up to next January plotted. So these are called contour plots. That means the points in this grid having equal values of the parameter total electron content are joined together. For example, so all along this circle, the electron content value is 40. All along this line, it is 30, and so on. So here, if you look at, say, at any particular month like March, then during the course of the day, it is a minimum value here indicated by the dashed curve around 4, between 4 and 5 o'clock. Then it starts increasing, 10, 20, 30, etc. reaches a maximum even more than 40 in the afternoon, around 14 hours, 15 hours. Then further it starts decreasing. So the diurnal variation can be understood from this. In addition, if you look at the variation in this direction, for example, the maximum value during the day, it attains again a focus. One focus is here, or maximum in the March, April months, that is the equinox season, and then another maximum in the September, October months here. So during the course of the year, it has 2 maximum, and that is called the semi-annual variation. If it has only 1 maximum during the course of the year, it will be called annual variation. So here it indicates a semi-annual variation, the maxima occurring during the equinox season. So this is the typical seasonal variation of the parameter electron content. This shows the same thing in a different way, in a sort of colorful way. So all these maxima here, they are occurring during, these are also measurements taken from not one station, but many stations, Trivandrum, Hyderabad, Delhi, Rajpur, etc. They are all in the Indian low latitude region. These are the months here, more than 1 year, 2004 and 2005 observations are put down here. These are the months, these are the local times. So this also shows the semi-annual variations, are measurements taken from Professor P.V.S. Ramarau's studies from Andhra University. Unfortunately, he is no more now with us. This again shows the variation of the electron density profile measured at a mid-latitude station. So mid-latitude electron density profile during different seasons marked as W winter, E equinox, and S summer. So these measurements are taken from a very sophisticated, very accurate measurement by an instrument called incoherent scatter radar. There are only very few, maybe 5 or 6 in the whole world. So, but they give very precise measurements, not only of electron density, also other parameters of the ionosphere. So, the typical nature that the electron density reaches a maximum at over 300, 350 kilometers is, of course, well seen here. And this graph is for solar maximum noontime condition. This is solar minimum noontime condition. Similarly, these are maximum and minimum, but midnight conditions. So the point here to note is, if you look at, say, for example, solar maximum noontime, this is the curve for summer, this is equinox, this is winter. The value of the electron content in winter, the peak value, is much higher than that of the summer. This is something unexpected. We expect during the summer the sunshine is more, and therefore the ionization should be more. But here it is occurring the other way around. In winter the ionization is more and summer ionization is less. This is true for both solar maximum and minimum during daytime. But at night time this is not there. Summer value is more than the winter value. Summer value is more than the winter value. So this phenomena occurring during the daytime, that the electron density is more during winter than summer, is called the winter anomaly, which occurs in the daytime. So this is this. So that we have discussed this so far, the diurnal and seasonal variation, and one anomalous feature of seasonal variation also we have seen. So now the long-term variation, that is as a result of the solar cycle or solar activity cycle. This picture may be well known for people who are interested in this field. So what this shows is basically how the solar activity varies during the course of the year. For example, this is showing measurements from 1880 to about 2010. So each vertical block here is a period of 10 years. So the solar, the sunspots, we all know, they are a measure of the solar activity. They start appearing at about 30-degree north and south latitudes of the sun in the beginning of a solar cycle, and then they slowly advance towards the equator. And so if you plot as a function of time the presence of the sunspots, you will, all of them will together form a diagram, something like that. So this is called the famous butterfly diagram. It looks like a colorful butterfly, which clearly indicates the sort of 11-year periodicity or 11-year solar cycle. This is also shown more clearly here in the clear periodic variations with a period of 11 years. This is here parameterized the total solar radiation. Here the sunspot number is plotted. So the 11-year cycle is clearly seen. If you take a long-term average, and then you will see a long-term trend also in the variation of the solar activity. So in the sun, there are variations of different periodicities, 11-year cycle, then long-term periodicities, and also some short-term variations. For example, due to the solar rotation, of course, the rotation period varies with latitude, but we can take an average rotation period of about 27 days. So the solar activity has a 27-day cycle, and similar periodicity can also be observed in ionosphere parameters. And still shorter period variations or periodicities are called transients variation, and that is due to phenomena like geomagnetic storms and substorms and things like that. So these are the kind of variations in the sun, and corresponding variations are observed in the ionosphere. So what is plotted here is the monthly variation of the total electron content TEC at an anomaly crust station. We will discuss little later what is anomaly and anomaly crust. The station by name Lumping in East Asia at different hours during showing seasonal and solar cycle varies. So here again, each vertical line is marked at an interval of about about 1 year. So this is 72, 73, 74, etc. Up to 1990 it is there. So each vertical line is 1 year. So the uppermost curve shows the sunspot number variation, which has a periodicity of about 11 years. And the similar, if you look at the mean curve of the TOEC value, then that also shows a similar 11-year cycle trend similar to the solar activity variation. And the actual TEC variation within 1 year, if you look at that, you get 2 cycles or 2 peaks within each year. That is the semi-annual variation we discussed earlier. And each curve is for a different hours, like 12 noon or 10 o'clock in the morning or afternoon and so on. So various at various local times, different local times, how the electron content varies over a long period of about 20 years here is shown here. So this is a clear indication of the solar activity variation. Now, this is also shown in a different way. If you look at the electron density profile during solar maximum and solar minimum, as indicated by the full line curves and the dotted line curve, there's a clear distinction between solar maximum and solar minimum. And also there is a clear distinction between day and night values of the or nature of the electron density profile. So this is so far we have discussed some of the aspects of the structure, and now we quickly go through some interesting phenomena that take place particularly at equatorial and low latitude ionosphere. One such is a sort of current system in the ionosphere, which is actually responsible for the geomagnetic field variation that we discussed earlier. So SQ current system they are called, S standing representing solar, and Q for quiet conditions. When the sun is quiet, because of the radiations coming from the sun, some current system is established, and another manifestation of that in the equatorial region is called equatorial electrojet. And also the phenomena equatorial anomaly, just we discussed, mentioned equatorial anomaly crust. So what is that? We will see that. Now, so these are driven basically by the solar thermal tides. You know, this is the sun here, the radiation is coming from the sun and it is heating up the atmosphere, which is that part of the hemisphere which is exposed to the sun. Well, this is not permanent because the earth is rotating. Different longitudes will come under the influence of that. But at any given time, this is the sunlit side, so that gets heated up and it expands. Therefore, it has a bulge like this, whereas at the night side, this bulge is not there. So to an observer in space, it looks like the heating or response bulge is fixed with respect to the sun because he is looking from space, from far away from the earth, and the planet is rotating beneath that. But to an observer on the ground, the bulge is moving westward because of the rotation of the earth at a speed of something like 2 pi radians per day. It is sometimes said that the bulge is migrating from one longitude to another longitude with the apparent motion of the sun. Actual motion is that of the earth, but it appears the sun is moving with the respect to the observer who is fixed on the planet. So this kind of variation of the heating can be represented by a graph, something like this. During the course of the day, the heating or the temperature increases, reaches a maximum during noon, and then it decreases. So this is nothing but approximate direct solar heating of the atmosphere over any location. So wherever the noon time occurs, where at that longitude maximum heating will take place. Now this is a periodic curve. Next day also the same thing will repeat. Next day it will repeat. So it's a periodic, but it is not a sinusoidal curve. But most of you may know that there is a technique called Fourier analysis or Fourier transform, by which such a periodic but non-sinusoidal variation can be split up into its periodic components. Here the fundamental period is 24 hours. So a fundamental component with a 24-hour or diurnal periodicity that is indicated by this curve, and then it has a harmonic or the semi-diurnal with a period of 12 hours component like that. So like that, the various harmonics, if you add all of them together, then you will get the original heating curve as indicated by the red curve here. So we using mathematical technique can divide or decompose it into its diurnal, semi-diurnal, even higher harmonic star diurnal, etc. components, and then understand what is the effect of these components in the atmosphere. So the heating is due to the various constituents absorbing solar radiation in the atmosphere. For example, below about 10 kilometer in the tropopause, it is the water vapor which absorbs solar radiation and gets produces heating. So this is the heating rate of heating versus the height. Then similarly, we know in the stratosphere there is ozone which absorbs UV radiation, harmful UV radiation, and that leads to heating there. And in the higher heights, in the thermosphere and the ionosphere, after the photoionization process, there is a lot of energy left with the incoming photon, and this energy is used for heating up that region. So various agencies are heating up various parts of the atmosphere. That is what is shown here. Now, so therefore, there are the winds, tidal winds. Tidal means they are driven by the tide, and therefore they have periodicities of the tide like diurnal and semi-diurnal, etc. So these kind of wind components, tidal wind components, are superposed atmospheric motions, and so corresponding to that, you will get an electric field by a process called dynamo action. So if V is the tidal wind velocity, here this illustrates the E region of the ionosphere, which has good conductivity. And so because of the interaction between the neutrals and the ionization, if the neutrals are moving with a velocity v, a part of that velocity will be imparted to the ions also. The ions also will therefore get some part of the tidal wind velocity v. And if the ions, which are conducting bodies, ions, ionization ions as well as electrons, if they are moving across a magnetic field, then by the principle of dynamo, an electric field will be generated. That is why it is called dynamo. So here, this graph illustrates the surface of the earth. This is the equatorial region. This is the magnetic field lines which are along the meridional direction going from north to south. And this is another field line starting at a higher latitude and going up to a higher apex height and so on. So a little away from the equator, the magnetic field has a small vertical component. Exactly over the equator it is horizontal, but little away it has a vertical component. So the vertical component of the wind, of the magnetic field B, crossing with a northward component or the meridional component of the tidal wind V, will give rise to an electric field which is in the eastward direction. So this is what is represented by this E here. So this is the meridional direction. The vertical direction is this, and the crossing of these two will be perpendicular to the plane of the figure indicated by the cross here. So the electric field is perpendicular to the plane of the figure, and the magnetic field lines are equipotentials for electrical field. So these electric field generated little away from the equator are conveyed along the magnetic field lines to the equatorial ionosphere. So you get your electric field here. This is how the electric field is generated. And the electric field in the E region drives a current because the E region has very good conductivity. And these currents are called dynamo currents. And it is these currents which are responsible for production of the electric current in that region. So the conductive structure of the ionosphere is shown here. There are, because in the presence of the magnetic field, the ionized medium becomes a anisotropic medium, and therefore the conductivity is not a scalar quantity. It is a tensor, and it has different components. And these are components are the sigma 1, sigma 0, sigma 2. And all of them, most of them, they reach a maximum at about 100 to 150 kilometers. So this is the dynamo region where you have maximum conductivity, and therefore a current J can be driven there, driven by the the electric field E generated by the dynamo action. So the dynamo electric field and the conductivity together gives rise to a current J. Conductivity profiles are shown here. So that resulting current J, if you look at globally, this is a picture as you see from the sun at the noon meridian. So the noon is here. This is the morning time. This is the sunset time. This is the North Pole. This is the South Pole. So if you look from the sun towards the earth during noon meridian, from the noon meridian, then you will see this kind of a structure, and then the currents flowing there can be represented by knowing the value of the conductivity parameter, the electric field generation, and so on. In fact, the currents can be calculated, and this kind of current contours can be generated. So the currents we see, they have a focus, or they reach a maximum at about 30° north latitude and at about 30° south latitude. So these currents set up like this because of the dynamo action is called the SQ current system. Is a global view of the average SQ current system. From one day to another day, it may vary slightly, but this is the average. And this is, therefore, as a result of these currents, we see here the current contours and the current lines are close by here. Therefore, the intensity of that will be more here. So near the equator, you will get more effect of this current on the magnetic field, or more increase of the magnetic field during the daytime. As you go away, that increase will be less and less. And at this point where this current and the reverse current, which is of opposite direction, they will cancel each other, and therefore there is no net effect of the magnetic field on the magnetic field here. So here the increase in the magnetic field will be zero, and here this focus also it will be zero. It will be maximum here. This is what is expected from this kind of current contours, and that kind of an observation is illustrated here. This is the observation from a chain of magnetic observatories, both Indian and Russian stations, so, ranging from about equator to about mid latitudes. So how the magnetic field during the course of the day, as observed by Balfour Stewart long ago, similar thing have been measured now at various locations. So each curve is from a particular location. So this is the equatorial location where as inferred from the current, the magnetic field variation should be largest, which is so. As you go to higher and higher altitudes, it becomes smaller, the amplitude of the variation smaller, and somewhere here it reverses the direction. Instead of increase, it becomes a decrease. Thereafter it is decrease. So somewhere between this curve and this curve, that is between about 32 and 39 degrees of latitude, should be the focus. So the current observations from various magnetic observatories very well matches with the concept of the dynamo mechanism and the current contours generated from there. So this is the SQ current, and because of some geometrical complications, these current at the equator it is inherently large, but it becomes even much larger over a small thin belt of latitudes plus or minus 3 degrees above the magnetic equator. So this is magnetic equator globally. It goes like this, and this red or pink color here indicates maximum current there, as indicated by the current the color code here. Maximum current here over a latitude range of plus or minus 3 degrees, and which is flowing at a height of about 100 kilometers. So this enhanced current flowing over the equator is known as the equatorial electrojet. That SQ current variation and the effect of the electrojet is represented in a different way. This is the increase during the course of the day, which is called the diurnal horizontal range, is measured at different latitudes from magnetic equator to plus or minus 60 degrees latitude. Okay, so the diurnal range is plotted here, and each point is an observation, and a mean curve is fitted to them. So here we can see this is the SQ focus where the increase is 0. It is increasing towards the equator. And if you actually fit a line between the points, you will get a curve like this. That's the actual observation. But if you sort of interpolate between these two wings, then it should be as represented by the dashed curve here. Meaning this dashed curve represents the actual current variation due to the SQ current, and this extra current over the or extra magnetic field increase over the magnetic equator plus or minus few degrees is representing the electrojet current. So this is the effect of the electrojet current, and this is the effect of the SQ current. So this is the actual measurements from the magnetic field, which is giving an indication of that. This is to explain that mechanism of the electrojet. So we said that the dynamo electric field is generated in the dynamo region, which is called between about 100 to 110 kilometers, which is called dynamo region, where the dynamo electric field is generated. So the primary electric field created by the tidal wind and the dynamo action is in the eastward direction with a typical value of about 0.5 millivolts per meter. So we should know that there is a magnetic field indicated by this in the northward direction. So under this condition, magnetic field is northward and electric field is eastward. The relevant conductivity of this region is called the Pedersen conductivity, which is sigma 1 in this. And so that drives this current, the Pedersen conductivity, and this electric field drives this eastward current. Sorry, this one, Pedersen current. And then there is another effect. As a result of this eastward electric field and the northward magnetic field, the plasma in this region would like to will be lifted up under the force called E cross B drift force. But this is a region which is vertically bound, because the E region profile, as we saw, it has a peak and then it decreases. So it is a sort of a slab of ionization. So it has boundaries. So the ions have less mobility. They are heavier. So they sit back at the bottom boundary, and the electrons move faster and reach the top boundary. With the result, a sort of polarization, charge separation is created, and that charge separation gives rise to an electric field in the vertical direction. So this vertical electric field, again crossing with the northward magnetic field, give rise to an increased current in the eastward direction. So this is the actual current due to the SQ, and this is the increased current due to this. So the electrojet is happening because of this additional phenomena of the vertical polarization electric field and the resulting increased Hall current, whose conductivity is sigma 2. So there are the Pedersen current, there is Hall current, and also there is another direct conductivity or sigma naught. So the effective conductivity there is given by sigma 1 plus sigma 2 square by sigma 1, and that is called cowling conductivity. So this conductivity is extremely large over a very small belt of equator. There only this vertical polarization field can be set up, because of the geometry, the exact perpendicularity between electric field and magnetic field. Beyond that, that effect is not there. That is the explanation of how the electrojet is formed and how much more intense current is formed there. So this is an artist rendition of this this electrojet current, the black ribbon, and showing at about 100 kilometer altitude. These are the different altitudes. And this electric field, when it is impressed onto the F region, it produces another phenomena called E cross B drift. The plasma is lifted up. At the same time, it has a tendency to diffuse along the magnetic field line because of the pressure gradient. And so the plasma moves, plasma contours, plasma line of motion are shown by the dashed curves. So just like a fountain, the plasma in the F region will be lifted up, then it will go to some higher heights, and then it will be diffused like a fountain. And this is called the fountain effect, and that causes the equatorial anomaly in the F region. So plasma fountain and anomaly. So it's an artist rendition of that. These this fountain will all converge at the latitudes of plus or minus 15 degrees. That is where the anomaly crust occurs. So that's a concept, but this is the actual measurements. You see the electron density plotted as a function of latitude. It is not maximizing over the dip equator here, but at a latitude plus or minus 30 degrees of dip, that is plus or minus 15 degrees of dip latitude. And it is different at different heights. At various heights, 200, 240, 280, 300, etc., the electron density is plotted with observations taken from both sides, both hemispheres, north and south. And so this is the actual observations of the equatorial anomaly. And this is an artist's rendition of what is happening. Because of the magnetic field geometry, the lifting is over the equator is exactly vertical. Slightly away, it is at an angle. So the ionization goes up because of this. And then because of the pressure gradient and the gravity effect, they are flowing down as a fountain and reaching a maximum in this region called the crust region. So this is what we saw here, and exactly the same thing is also indicated by measurements. These are actually electron density measurement contours in a vertical plane, altitude versus latitude. So you see here, this is the dip latitude. Here, electron density is minimum, it is less than 5.8, whereas a little away, it is reaching 6.2, 6.4, etc. So whatever is shown by the previous artistic rendition, the same thing is illustrated by proved by the measurements here of electron density as a function of height and as a function of latitude and contours generated from there. So this is a further illustration of the equatorial ionization anomaly. So I think we conclude here in this presentation. Materials from scientific research papers, books and websites have been used. I am thankful to all these